Hi friends, welcome to my channel. Let's have a look at a newly appeared problem, problem 2607. Make K-Subarray Sums Equal. In this video, we are going to explain a solution based on the concept congruence. So this is a mathematical concept, but it's sort of elementary. Here, we are given a zero-indexed integer array called array and an integer k. So the array is circular, right? So here, this explains what's a circular array. So it's in our it's with the same as with our intuition. So we can do the following operations to operation any number of times. Pick any element from array and increase or decrease it by 1. So we are required to return the minimum number of operations such that the sum of each subarray of length k is equal. So here, a subarray is a contiguous part of the array. This is the main problem statement. And here are two examples. In the first example, actually, we can change 4 to be 3. So then we're going to have the length 2 subarray sums are all 1 plus 3, that is 4, right? So we need one operation. That's why we have an output that is 1. In the second example, so the output is 5. Here, basically, we change all the numbers to be 5. So to change 2 to 5, we need 3 operations. And then here, from 7 to 5, we need 2 operations again, more. So we have 3 plus 2, that is 5 for the output. So we're going to digest this example and or generic case in the explanation. So before we look at the explanation, let's look at the constraints. First, the k is bounded below by 1 and less than or equal to the array length, which is bounded by the number 10 to the power 5. So this number 10 to the power 5 is decent large, and it defines the problem size upper bound. Secondly, so the elements in the array is bounded below by 1 and bounded above by 10 to the power 9. So with that said, basically we can go to the treatment or analysis. So here actually our treatment is based on the congruence. So we actually use a very simple part of this congruence. So this concept actually can derive involved in lots of theories, mathematical theorems in elementary number theory. So it can be very complicated if we dig deeper. So here we just need to solve this problem. We are not going to give a proof, though it's not. We are not going to give a proof for the congruence involved, but you know the proof is still not hard. So the requirement in this problem actually partitions the indices into clusters, or we can see we partitioned the corresponding elements. Within each cluster, all the corresponding elements shall be equal. So this is our overall guiding principle or strategy. So let's use the first example and then change k and 3 from 2 to 3 or 3 to 2 to digest the requirement or this sentence. So here let's use the array in example 1, and we can call it A0, A1, A2, A3. So we actually abstract it a little bit. So here we have a k equals 3. So here we pick a specific key is just to fix the idea, right? And to make length k sum to be equal, let's see, this is the length 3, right? So we are going to have this sum, A0 plus A1 plus A2. And then this is also 1. We shift to the right by 1. Then this is A1, A2, A3. So if we let this 2 equal, so actually it yields that A0 must equal to A3. So similarly, we consider another one. So A1, A2, A3, right? Then we should it should equal to A2, A3, A0 due to the problem requirement. And then we are going to have A1 equals A0. So you can write other relations to get A3 equals A1 and A3 equals A2. So overall, if we connect all together, so we see that A0, A1, A2, A3 must be equal. So in other words, so this requirement when k equals 3 induces a single cluster, so 0, 1, 2, 3 for the indices. So we need to use as less operations as possible to make all the corresponding 4 elements equal if k equals 3. So as in example 2, so we make it equal to 5. Actually 5 is nothing but the media of this array or list. So now let's continue to digest. Let's see the same array with k equals 2. Then the requirement is that a length 2 subarray sum must be equal. So if we check this, A0 plus A1 equals A1 plus A2. So this yields that A0 equals A2, right? So if you continue write this equality relations, we are going to get A1 equals A3. Then again, from this one we get A2 equals A0, and the last one we get A3 equals A1. So if we look at these relations, so we see that the indices actually are partitioned into 2 clusters. One is 0, 2, because 0, 2, the corresponding elements should be the same. And also 1, 3. And for the corresponding elements, they must be the same or equal. So we need to use as less operations as possible to make elements in each cluster equal. So that's the main strategy. So let's recall this sentence. So the requirement in this problem actually partitions the indices or corresponding elements into clusters. And within each clusters, all the corresponding elements shall be equal. So here is the question: how to get the clusters? So here actually involves some math. I see still some elementary math. So we can let D equals the greatest common divisor of n and k. N is the length of the array, and k is the k here given in this problem. So then, starting from a fixed index C0, then indices of the form I0 plus a constant multiple of D lie in the same group or cluster. So this can be easily proved by congruence equations. So this is actually not hard at all. So in other words, so the 2 indices ij lie in the same cluster if and only if I minus j equals 0 in the sense of modulo D. So if we want to use plain English, it means that the difference between I and j is a multiple of D. So if actually this is what this equation says. So that's about it for this problem. So next, our task will be partition the indices or the corresponding elements into clusters, and then make all the cluster elements in a single each cluster equal, and then in the process we count the needed operations. So that's the logic. Now let's look at the coding. So as for the coding, actually it's very straightforward. So first let's get the length of this array. So this is just for convenience. Then let's get the GCD of the n and k. So here we can call math GCD. So we get n and k. Or if you like, we can write our own utility function. So actually you can check our YouTube channel. So we have some problems in which we wrote our own utility function to get a GCD. This is one part. So next, let's initialize a result variable. So this is a counting variable, right? Counting the number of needed operations to make the element equal in each cluster. And then we're going to do iteration. So for I in range D, right? Then we're going to get the corresponding clusters. And then we can do this. So basically array G, right? For G in range, so we can start from I, right? And then end at index n minus 1. So we write n here. So we can pass a step variable. So we pass the step d. So as here, right? I naught plus kd. That is k is an integer multiple, and this. So this means we start from I, then we consider I plus kd, right? Actually, this is not sorted. So because we want to compute the media, so let's do this. We do the sortage. And then the media for this problem, we can actually do it very rough. So because it's sorted, we can pick the middle elements, right? So we can do this temp length of temp over 2, right? So this is the media elements. So then what we are going to do, so for this cluster temp, so we want to do a sum. So we want to check the distance of each number y and the media in this for y in temp, right? So this is the contribution or needed operation for this cluster. So once we computed all the clusters, and then we're going to return the result, right? So because the GCD of n at the k is d, so right, so we have at most d clusters, right? So with that said, I guess we are done the coding part. So this coding actually encodes the above strategy and analysis. So we can understand this as a translation of the above explanation. So now let's do a test. Yeah, it passes the first example. Now let's also check the second example. Yeah, it passes the second example. Now let's look at the generic case. Yeah, it passes all the generic cases. So that's basically about it for this specific problem. So here, before we end this video, let me make 2 comments. So the first comment, so there may be remarks. The first one is that, so here there's some mathematical property. Let's see. We have some integers, say a times x equals b in the sense of modulo say k, right? And then this problem, this equation is solvable in the sense of congruence if and only if. So it's solvable if and only if the GCD of n and k is a factor of this b, right? So essentially we are using this one, but if you are interested, you can try to prove that. So if you have some mathematical background, so this is actually very straightforward. So this is the one thing. So another thing is when we compute the median for a sorted list. So basically, if the list contains odd number of elements, so we just pick the middle one. If it contains an even number of elements, so we can choose the mean, right? So for example, here. So if we have 1, 2, 3, so the media will be 2, right? So now if we have 1, 2, 3, and 4, right? So the media will be actually, if we do not consider the integer, so we can do 2 plus 3. This is the 2 middle elements. Then divide by 2, that is 2.5. But in this problem, we need to do some rounding to make it 2 or 3. So here we didn't consider the length. So if we consider the length, it might be also good. So let's see, m equals the length of temp, right? So if m modulo 2 is 1, in other words, it's odd. So like this one. So we just need to do this. So media will be this. Otherwise, so here the middle is corresponding to index 1, that is 3 integer division by 2. So here we are using the average of, so here's 4. 4 divided by 2 is 2, right? 2 and 2 minus 1. So let's see. We're going to use the median will be the temp. So here m over 2, then plus temp m over 2 minus 1, right? So, but we need to make sure this is non-negative. So, for example, if m just contains one element, right? Let's see. In this case, because if m equals 1, so we also have this if, right? So this actually covered, so we can do this. So media, and then we can choose, we can do division by 2. So we can do integer division, right? And then let's see. Let's do a check. Yeah, it passes. And then generic case. Yeah, it passes. But now, because it works in this case, so I'm going to just ignore this, and then I'm going to write like this, just to content ourselves with this not so rigorous solution. So now let's do a final test. Yeah. I guess with that said, that's about it for this video. Thank you.